Hi, class. So, in this example, what we're going to do is we're going to look at a full-blown study, kind of from beginning to end, and walk through each of the steps of how you test a hypothesis. So this is kind of like, you can almost think of this as like the culmination of everything that we've been learning in statistics, because a lot of those concepts are going to come up and appear within this one example. So I think it's a really good way to kind of sit down and think back on all the different things that we've learned so far. So the way that this looks is, so let's say that last year some study was done, right? So there was a study done, and in that study, a group of researchers found that, let's say that they were studying, right, the population they were interested in. Let's say that these are college freshmen, and these researchers took a sample, right? They took a sample of these folks, and they found in their sample last year that on average, so they're saying that their sample average last year was that the amount, so let's say that they're studying the amount of money, so the number of dollars spent on fast food per week, right? So they found that last year that a college freshman spent an average of $25 per week on fast food last year. With, so let's say that they had a standard deviation of, $8 per week. Okay, and so that's kind of the background information. Okay, study was done last year on these college freshmen, and they found that on average they spent $25 a week. So that's their sample mean, and with a standard deviation of $8. So they go back in and they say, okay, so they look at the pool of college freshmen this year. So right, here's their population again, and they take a sample again, and then let's say that this year their sample mean is $18 per week. Okay. And so let's say that this year their sample size was 130 people, and with a standard deviation of, let's say that this time it was $7. Okay. Okay, so this is the data, right? And this is kind of the important thing to look at. So took a sample last year, this is what they found. Took a sample this year, this is what they found. And so the question that we're asking here is, has the mean really changed, right? Has the mean really changed? So they took a sample last year, $25, this year, $18. And so you might look at this and say, hey, look, this is great. College freshmen are spending less money on fast food this year than they did last year. That's awesome. But is there really a change? Or is this just a different, right? Because when you look at the sampling distribution of means, right, you have some average, but then you also have like every other possibility, right? Is this just one of the possibilities and that, 25 was another one? Is the population really the same? And we're just looking at two different samples. So is there a way to kind of test and to look at whether or not the average has really changed? And so that's kind of what these tests are for. So for example, let's say that we want to know, so it's like a question is has the mean really changed? Okay, so now we're going to look at our hypotheses. So the null hypothesis is going to be, we're going to say, okay, that the mean of the population, so last year was 25, and my alternative hypothesis, the one that I think is true, is, so let's say that I think that it hasn't changed. Let's say that I think that, nope, it hasn't changed. It's still $25, even though the sample I took was low. So now what I want to do is I want to go in and I want to try and reject this, right? If I can reject this, that the mean is $25, then that would allow me to accept this, which says that the mean is not $25, that it's different, okay? And I can look at this and say, okay, so look, I chose this, so what does that mean? Am I a one-tailed test? Am I a two-tailed test? If you look at one of the previous videos that talks about hypotheses, this symbol here lets us know that it's a two-tailed test. So if you're looking at a distribution, that means that you're testing both sides, both of the extreme tails on that distribution, not just one. Then the other thing we need to set up at the beginning of our study is we need to say, okay, what's my accepted level of risk? And so standard for most studies, your alpha or your significance level, we set at 0.05, okay? So we say, all right, this is my significance level, and so I'm saying that this is the amount of risk that I'm willing to take, meaning that I'm willing to risk a 5% chance of my study being wrong, or a 5% chance of making a type 1 error, okay? So I now have everything set up to go through and give this thing a try. My sample size is good, right? I'm over 30. I've set up my hypotheses with the alternative hypothesis in opposition to the mean. I know what type of test I'm doing, and I have a significance value or an alpha level set. Okay, so let's dig into this. So the next step here is we need to say, okay, well, if this is my significance value, well, then what is the critical value going to be? Okay, and so one of the ways of looking at this is I do have a separate video on this that shows that, you know, given any alpha level, you can go through and find whatever critical value you want using the charts. But that would take, that takes some time. And the nice thing is like industry standards, so we have this table here, and so these right here are the alpha levels. These are kind of the standard alpha levels. A 10% risk, which is high. Most researchers, that's too much risk to accept. So really, you live in this space, either this is a 5% risk, or you live in this space, which is a 1% risk. So like studies that need to be really careful, they live here. Studies that, like a normal study lives here, and if you really wanted to be flaky, you might, accept a 10% risk. This one, by the way, is 2%. Much more rare. Most of the time studies live here in this space or here in this space. And so with that being the case, we can just, if you just use this table, this tells you, based on the type of, right, are you doing a left-tailed test, a right-tailed test, or a two-tailed test? And we already said that we're doing the two-tailed test. So here are our critical values. Okay? I could go and look everything up on the chart and set up the distribution and say, okay, look, if I have 5%, then that means I have 2.5% here and 2.5% here, which matches a proportion of 0.025, and then go to the table and find the z-score that fits that, and I would say, lo and behold, look, the z-score that fits that is this number. But because 5% is basically an industry standard, we just know that the critical value for an alpha level of 0.05 is plus or minus 1.96, okay? So what that means is, in my distribution, I have plus, 1.96? Is that what I said? Yes. Plus 1.96 over here and minus 1.96. And by the way, this thing that I'm drawing here, this is the sampling distribution of means. And I'm testing whether or not the mean that I found in my population, right? So the sample that I just took, I got a mean of $18 per week. The mean that I'm testing it against is the mean from the previous year's study. So that mean actually is sitting right here in the middle of this, $25. And I'm testing to see, okay, if the real mean is $25, well, where does $18 fit? So I know I'm going to be on this side of it, okay? If my $18 lands over here, then I fail to reject, right? That would mean I would say, hey, this $18 is too close to the 25 for me to say that it's different. It's too close. But if that $18 value lands out over here in the region of rejection, then I can say, hey, look, this value of 18 is different enough from 25 based on my statistics to say that to reject the null and accept the alternative hypothesis that they are in fact not the same. So that's kind of the space that we're living in here right now. Okay. So again, my critical value is 1.96. Shows where my region of rejection is. So that's right here, and all of this right here. But I mean, the funny thing is I kind of don't even need to worry about this side because I already know that 18 is less than 25, so I'm gonna end up over here somewhere, okay? So I'm really just kind of focusing on the left side of this distribution. So let's see where I end up, okay? I've marked my critical value that I took from this table of already found numbers. Because I know I'm doing the two-tailed test, so I know I'm just right here, and I can just be really safe in the fact that this here is the value that I want. So, oops. Okay, so then, okay, what's next? Okay, so we need to calculate our test statistic, which means it's kind of like I need to find out, well, what's the z-score for this 18? Is that z-score going to put it here, or is that z-score going to put it over here? Right? I mean, that's like the whole point of all of this. So to do that, to calculate that z, I need to take the sample mean that I got, subtract it from the mean that correlates to the null hypothesis, that's why there's that little knot there, and then divide that by the standard error. Okay? So, running our numbers here, so my current sample is 18 minus 25, right? I'm trying to see, is 18 really different than 25? And then divide that by the standard error. Okay, so what was my, so this says, hey, okay, so I had a standard deviation of 7 with a sample size of 130. Okay, standard deviation of 7 divided by the square root of 130. Okay, so I have all of this, and I need to calculate it. My recommendation, by the way, be so careful how you enter this into your calculator. If you're using, make sure you put the whole numerator in parentheses, make sure you put the whole denominator in parentheses. That's going to be the easiest way to stay safe with something like this. So I'm going to do 18 minus 25, quantity divided by quantity, 7, divided by the square root of 130, and I get a z-score of minus 11.4. Huge, huge z-score. That's funny, right? So if you run this back over here, so that's on the negative side, right? My critical value was right here at minus 1.96. So here, let me redraw my distributions. It's like, here's the distribution. So imagine that right here is this minus 1.96, and this score of minus 11.4 is way out here. Minus 11.4. Meaning that I am deep into the region of rejection. So I can actually with a lot of confidence say that yes, in fact, this 18 is different than, well, I mean, okay, so I guess that's really not how you would say these things. So number one, I would look back at my study and I'll say, okay, let's come back here. I was in the region of rejection, so guess what? I can reject the H naught, which means that I'm accepting this. And so all I'm saying in this study is that my alternative hypothesis, which says that the mean is not $25 a year. Okay? The mean is not $25 a year. It's no longer that. I can say with a ton of confidence that that statement is true, right? There is enough evidence to conclude that the mean has changed. Okay? And that's all that I'm saying. I'm not saying that the actual average is 18. That is not what I'm saying. What I am saying is that the mean has changed and that it is no longer 25. That's what I can say. Does that make sense? Do you see the difference there? This study, I'm not trying to prove that the true average of the population is 18. All I'm showing here is that it's not 25 anymore. Okay? And based on how large this z-score is, I can actually say with quite a bit of confidence that it's much less than $25 per week that the college freshmen are spending on fast food. Okay. One of the reasons why it was pushed so far out was because my sample size was so large. And that's one of the really nice things about having a large sample size. As long as you randomly drew it, it gives the results of your study a lot of power at this point in the process. So that's how all this works. Again, kind of looking at this step by step. We started at looking at the given information from like a previous study or something like that, saying, hey, look, here's what they said the average was. Here's the information from my new study. And I'm going to walk this through a process. I pick an alternative a null hypothesis. I choose an alternative hypothesis, and this is the thing that I actually believe. I set a significance level. I then use that significance level to find my test statistic. Or not the test statistic, but a critical value. Okay, and we ended up choosing this one because we were at a 5% in a two-tailed test. And then I use that to draw and build the distribution. I then calculate the test statistic. I run back to my graph and make a comparison to see, well, where am I in relation to the critical value, right? And then we kind of looked at and saw right here that we're way to the left of the critical value, right? All of this is region of rejection. It means that I can reject the null hypothesis. And we're deep, deep, deep into the region of rejection. So I can go back and I can say, yes, reject the null, which means I can say that there is enough evidence to conclude that the mean has changed, which is all that I'm saying. All right? Let me know if you have any more questions about this. Get a lot of practice in, and good luck on this week's module and next week as you continue working. Thanks, everybody. Bye.